with a Wi-Fi link. You configure your access point. So in this case, my EPC is running as an access point. And once you've gone through this configuration step from a commercial game, then you can run all your open source software on the Nintendo DS. So as a conclusion of this Nintendo DS part, and then I will have to hurry up on the PSP part, we have a functional TCP/IP stack for connecting, running a shell, acquiring data, and controlling pieces of software. Now, so I really think that the Nintendo DS is the best piece of hardware that you can find in your drawers for learning how to develop from scratch embedded devices, including the software and the hardware part. Historically, we started with the PSP, simply because I got a PSP one Christmas earlier than the Nintendo DS. And the PSP is a much newer game console, which claims to be much better. And actually, at the end of the day, there's much fewer things that you can do with it. So far, we've seen that the NDS is an ARM architecture. Now we're switching to a MIPS architecture. And one thing that I emphasize in teaching embedded devices is don't be limited by the tools you have available. When you're using proprietary tools, you're spending a few $1,000s on a compiler, and the day you want to switch to another project, you will select your new hardware depending on the compilers that you have. If you learn how to use the trio GCC, binutils, and ulib, you're no longer limited by the hardware because this set of tools will simply cross-compile Linux or any kind of software to whatever CPU you're familiar with, Alpha, Spark, MIPS, ARM, of course, x86, Intel. So by learning how to use these things, in the beginning it's a little bit more difficult than buying a tool, a ready-made tool from a vendor. But once you learn to do this, you're no longer limited by what hardware. You're only limited by your imagination and your ability to cross-compile a piece of software for this hardware that you've selected. Now, in this case, we have a MIPS 4 architecture with 32 megabyte RAM, which is much more comfortable for running UC Linux. And our purpose about a year ago was to run UC Linux on this system. Now, this was after someone from the US, whose name I'm unable to pronounce, Chris Mulder something, Mulderhan or something, had done most of the work. And his problem was that he did not have a coherent tool chain for generating both the Linux kernel and its applications. He could compile the Linux kernel, boot the Linux kernel, and then it crashed. All his applications were incompatible with his Linux kernel. And before I get into the details of compiling the Linux kernel, you should know that running a game on the PSP is a little bit more involved than on the NDS because Sony will not allow you to run games from your memory stick, from the memory stick that you insert here. You're only allowed to run games from the disk, the optical disk. So what you have to do is downgrade the software in the flash memory of a PSP so that you're allowed to run games or your programs from the memory stick. And you have to go back to a time where Sony was not so paranoid and go back to an older firmware where you can do this. But this is a little bit dangerous because if you fail in this flashing procedure, your PSP is so-called bricked. It's no use anymore. This is evolving. I think now it's a much safer procedure. And then our operating system will appear as a game on the Nintendo DS. So if you're familiar with a PC, the first thing a PC does is initialize its hardware, and that's what's done by the BIOS, and then you have Grub or Lilo loading the operating system. Here you have to write your own loader so that the operating system is loaded in the memory of a PSP. And this is what you do here. You have, again, an address space, the area of the memory that is dedicated to the RAM. So this RAM is where you will put your operating system. You will remove the Sony operating system and replace it with a Linux operating system. So what you're doing here is you start by identifying this RAM area, and this, again, is something that you can only know from the datasheet of the PSP or by reverse engineering. You will open your file, and since we have still access to the Sony operating system, we can access to the memory stick and read the file. We uncompress it, load it into memory, initialize a few pieces of hardware using the Sony operating system, and then we jump to Linux and start running Linux. So I mentioned to you that this is loading Linux, and once you've loaded Linux, Linux wants to run init, and after it's run init, it will start its shell and its user space operating system. And the main issue is to have a coherent tool chain for generating the Linux kernel and its tools. And the main challenge that was met by my friend here, Simon, who's in the room, and one of my co-authors, is to port the linker, which used to generate ELF binaries, into the format that is recognized by UC Linux, which is binary flat. Binary flat format is a smaller format which contains less information than ELF, but is faster, smaller, and easier to load. And the main challenge was to take the binary flat converter, ELF to binary flat converter, and to insert it into the MIPS toolchain, which means that before we did this, to my knowledge, GCC was only able to generate MIPS software for MMU-equipped processor, and now it can generate software for MMU-less MIPS architecture. And then I tell you that I enjoy working with GCC, Binutils, Newlib, but the fact is that now generating a full toolchain is becoming so complex that you need some kind of environment to help you with these tasks. One of these tasks, yesterday we've seen on the OpenARM presentation, something like MDebian, embedded Debian. That's too complex for me. I'm still familiar with my free tools, and I'm trying to learn how to use buildroot. Buildroot is simply a set of makefiles and a set of tools for helping you generating your board support package. And most important, it will generate the tool chain for compiling both the kernel and the applications, which means that necessarily these two pieces of software will be coherent. They will pass arguments in the right way. And so our main contribution in this work was generating a buildroot environment compatible with the MMU-less MIPS as used in the PSP. And at the end of the day, what you get is Linux running on a PlayStation Portable with your shell here. And unfortunately, I will no longer be able to discuss hardware because there is simply no hardware port available on the PSP. The only piece of hardware that you have available is the serial connector next to the headphone jack. And what you can do is connect RS-232 level converter so that instead of typing using the on-screen keyboard tool that is provided on the web for PSP, you can type your commands from your PC and the PSP appears as a terminal. But that's meaningless. Why have a handheld game console if you need a PC to type commands? That's absolutely useless. So yeah, that's, for example, typing uname -a to show that Linux is running on this piece of software, ls to show that your file system is running. And once you know how to reach serial port, and I'm running out of time to discuss in detail how you inject commands that you type on the serial port in the keyboard layer, basically what you can do is replace this PC that you had typing commands using a dedicated microcontroller to convert PS2 commands into RS-232 signals, and this tells you that you can put a keyboard onto your Nintendo DS, on your PSP. Here you don't have a PC anymore. This PS2 keyboard is directly connected to a microcontroller, and the microcontroller is sending RS-232 commands, and these RS-232 commands here into a VI editor will allow you to type your programs into the PSP. So basically on the PSP, you have your piece of software, you have Linux running, but since you have no hardware available, because I should emphasize that there has been no, to my knowledge, successful reverse engineering of the Wi-Fi link or the USB link on the PSP, basically the only thing you can do nowadays is have an external microcontroller for all the dedicated hardware access and send or read commands through the RS-2